All right, this next set of notes goes over two different forms of energy besides GPE. Those are KE and SPE. They stand for kinetic energy and spring potential energy. Also within this set of notes, we will go over the concept of energy conservation, which deals with the fact that energy just transfers forms. You never really make it or lose it. First form, KE or kinetic energy, simply put is the energy of motion. So the larger an object that you have and the faster it goes, the more energy of motion you'll have. If you look at the formula here, the M stands for mass, V stands for velocity. So any object that has any motion whatsoever will have kinetic energy. What's of important note here is the square on velocity. So if you were to double the velocity of an object, its kinetic energy will actually increase by a factor of 4. For instance, if its speed was tripled, then its kinetic energy would go up by a factor of 9. So the amount of velocity is very important in figuring out how much kinetic energy it possesses. So you could have objects with small mass. They could have a high kinetic energy if their velocity is quite high, example being a bullet. But you can also have objects moving very slow that have a lot of kinetic energy if their mass is quite large. It would be very difficult to stop a freighter coming at you even at 1 mile per hour. All right. A numerical example of calculating kinetic energy. Here, a person, an 80 kilogram sprinter, moving at a speed of 10 meters per second. What would his kinetic energy be? Notice here the 100 meter dash is just extra information, right? That doesn't tell you how fast he's moving, right? Doesn't tell you the mass of the person. So that's just extra info. Here, if we plugged in 80 kilograms and 10 meters per second and multiply all those things through, we would arrive at an energy of 4,000 joules. Please note that the units of kinetic energy are joules, just like GPE and just like work. Technically, a kilogram times a meter per second squared is a newton. So you wind up having newtons times meters here again, which you guys know is equivalent to a joule. Now, the conservation of energy, simply stated that energy cannot be created or destroyed. It can transfer from one form to another, but the amount of energy that you have does not change. Right? In a lot of realistic examples, it might appear that energy is lost, but usually that is lost in the form of heat energy due to friction. Right? If we're doing any problems in here, we'll most likely be assuming frictionless conditions, so that you can make the assumption that there is a total energy transfer from one form to another. An example of that here is an object in free fall. So if you were to have an object at a really high height, in this case, object has a potential energy of 10,000 joules, starts out at a speed of 0, so its kinetic is nothing. As the object falls and the height decreases, right? Notice the potential energy drops, but as the object falls, they're picking up speed. So that loss of potential energy is continually turning into an increasing kinetic. So by the time the object gets to the very bottom, notice that all of the potential has transferred into kinetic, and at every moment the total energy is 10,000, right? That never changes throughout the entire fall. Here's an example of utilizing the conservation of energy. Here we have a free fall problem from a height of 45 meters. Question is how fast the object would be going at the moment it gets to the ground. All right, in utilizing the conservation of energy, we know that the potential energy at the top is literally just going to turn into kinetic at the bottom. So we can kind of set our two formulas equal to each other here. Notice that the mass is on each side of the equation. In essence, it cancels out. And you know from a free fall situation, it doesn't matter how heavy the object is, right? It depends on how high it is and how much speed it gains, right? If you work through this here, notice we get a speed of 30 meters per second, right? Earlier in the year, we would have had to figure out the time in the air, and if you work through it here, it would be 3 seconds, and then you'd eventually get to the 30 meters per second for the final vertical speed. Now, the other type of energy we're looking at here, and we will also be looking at in the lab in the upcoming days, is spring potential energy. We're going to use the acronym SPE for it. It is sometimes referred to as elastic potential energy. Right? It's the energy that is stored in an elastic material. We've specifically looked at springs earlier in the year, and we will be utilizing a spring in our lab on Wednesday and Thursday. Right? Now, the work done by a force to stretch a spring, right, is going to give it its potential energy. All right? If we go back to Hooke's law, that amount of force is equal to its spring constant times the distance stretched. Now, when you're stretching a spring, it's very easy to stretch it at the beginning, right? Because its distance isn't very much, so the force is small. But as you stretch it more and more and more, the force you have to apply ramps up. So when you go to find the work done by this force, you have to use the average force. All right, so that's where the 1/2 comes from in this formula. So Kx is literally the amount of force required to stretch it its maximum distance. So the average force is 1/2 of that. And when you multiply that average force by its distance, you wind up getting the distance squared. All right, so you wind up getting a formula that's highlighted in yellow here of 1/2 Kx squared. Right? If you look at the units, right, it's still energy. We should be getting joules for the units. And if you remember, the units of spring constant are newtons per meter. If we have the stretch distance squared, its units are meters squared. When you multiply these two, one of the meters cancel. We're left with Newton meters, which, as you've learned, is the unit of joules. The last part of these notes is a spring potential energy example problem. This might look similar to what we did with Hooke's law earlier in the year. Here we have a spring that's stretched 2 centimeters when a force of 50 newtons is applied. All right. Before we can use the spring potential energy formula, we have to find out what the spring constant, or K value, is first. If we want to work in metric units, base metric units, we need to convert our 2 centimeters into 0.02 meters. Here we have a ratio of 50 newtons to 0.02 meters, which yields a spring constant of 2,500 newtons per meter. Now we're set up to use the spring potential energy formula. We have 1/2 of the K value, right, the spring constant, multiplied by the stretch distance squared. If you work through that correctly, you will get a energy of approximately 5 joules. All right. Now, when you have a spring that is stretched or compressed, when it's released and returns to its original position, that stored energy is released and turns into kinetic, right? It's not lost, right? It just turns into a different form. Here's another example where we can incorporate all 3 types of energy that we have looked at so far. If you've ever seen those little spring-loaded pop-up toys, all right, when you release them, they fire and then raise, into the air to a certain height. So if you look at that situation, you're starting with energy stored in a spring. It's released. The toy acquires motion, speed, right? And as it rises, it slows down as the energy is restored in the form of GPE, right? So if this spring toy had 1 joule of energy stored in its spring, it'll turn into kinetic, which will eventually turn into GPE, All right, so if we knew the mass of the object, which is provided here, right, it's a 1/2 kilogram, we can set 1 joule equal to its GPE at the peak and work backwards to figure out to which height it rose. In this case, you would get to 0.2 meters, right, if you did your algebra correctly, which is equivalent to 20 centimeters. Right? Please keep in mind all of these types of energy, because in the lab tomorrow and Thursday you will be utilizing SPE, KE, as well as GPE.